Hi, I'm Jeff Wittick, Head of Products at Ampere Computing. We are a passionate, experienced team committed to building the next generation processors designed for the cloud and edge. When we talk about the cloud, we're focused on both the hyperscale clouds as well as the emerging edge cloud as well. Looking back over the last 10 or 15 years, the needs of the cloud have dramatically diverged from the needs of traditional enterprise IT. A number of changes have occurred. The software ecosystem has changed as developers have moved towards cloud-native applications and the associated shift towards containers and microservices. There's been a large growth in the edge, which necessitates distributed computing across your entire infrastructure, and also demands increases in power efficiency, as well as additional demands to increase the density of compute for large hyperscalers. Also, with the emergence and the growth in AI and machine learning, this has increased the need for compute capabilities across the entire infrastructure. And lastly, as cloud service providers have optimized their infrastructures, they've moved towards more and more customized architectures, especially those that are heterogeneous. They're starting to deploy GPUs for AI training, they're using SmartNICs for network offload, and increasingly, they're looking at using non-x86 CPUs in their infrastructure as well. Now, looking back over the last 10 or 12 years, the current solutions just don't meet the needs of the cloud. From 2008 to 2013, x86 processors were able to increase performance by 60% annually and improve performance per watt at the same rate. However, since 2013, the rate of innovation has slowed down dramatically. Not only has the rate of improvement in performance slowed, but the performance per watt increases have similarly slowed as more and more power is needed to increase performance year after year. And power consumption is more than just a concern around density and OpEx. It's a global issue as well. Today, data centers consume about 3% of the worldwide energy. However, experts predict that could grow to as much as 11% over the next decade. Now, over the last 5 or 10 years, that 3% number has been able to be maintained because of innovations in data center efficiency as PUE has decreased. However, all of the easy things have been done. We need new innovation in order to continue to maintain the current levels of energy consumption. And when we look at greenhouse gas emissions, the airline industry is currently regarded as a major offender. However, data centers today currently emit as much greenhouse gas every year as the airline industry. We need power efficient processors in order to continue to improve those numbers over time. At Ampere, when we look at the needs of the modern cloud, we think of 3 key areas. 1, the cloud needs predictable high performance. 2, it needs scalability across the entire platform, from cores to I/O to memory. And 3, it needs power efficiency and density. In order to meet these needs, we've developed the world's first cloud-native processor, the Ampere Altra processor. This is the first CPU that was designed from the ground up for the unique needs of the modern cloud. Our Ampere Altra processor has 80 cores to deliver high performance, exceeding any other CPU in the market. It's scalable across I/O and across memory with more I/O bandwidth and more memory bandwidth than any other processor in the server market. And it's the most power efficient server processor in the market as well from a processor perspective. The Ampere Altra processor has 80 64-bit ARM cores. Each core is able to run at a sustained 3 GHz. That's 3 GHz across all cores across a wide variety of cloud workloads. Again, it's important that we deliver consistent performance, regardless of how many users are on the platform and regardless of what workloads are actually running. In addition to the consistent turbo performance that the Ampere Altra processor provides, We've also designed the core to be single-threaded in order to provide better performance and security isolation. The 80 cores are connected by a high-bandwidth mesh interconnect on a monolithic die. We specifically chose to design this generation of processors with a monolithic die in order to avoid bottlenecks that occur in current multi-chip architectures. We've also emphasized a very large cache, especially our L1 and L2 private caches. We have a 64K instruction and data L1 cache, and a full megabyte of private cache in the L2. You don't have to worry about the resource contention from the various cores because the L1 and the L2 cache are private and not shared. Additionally, we chose to optimize these caches because they're closer to the core, which provides higher performance and lower latency. The Ampere Altra processor also has a single 32 meg shared system level cache. Additionally, the Ampere Altra processor has two 128-bit SIMD units for vector and floating point performance, since inference performance is becoming increasingly important as AI inference is being done across a wide variety of servers and infrastructure. We've also introduced int8 and FP16 support for those who are using those numerical formats for inference performance improvement. Now, expanding on the single-threaded approach, we specifically designed our cores to avoid noisy neighbor issues. This can show up in either performance or in security. And by having single-threaded cores where no threads are sharing the execution engine, the registers, or the L1 or the L2 cache, we avoid this type of resource contention. And we're able to better provide security isolation by reducing the attack surface. This has become a particularly problematic issue over the last couple of years with some of the side channel attacks that have become prevalent in the industry. In addition to resource isolation, the single-threaded cores provide more consistent execution of instructions. In the case of a multi-threaded course, two threads are executing at any given time. These threads typically belong to two different users on a single system. And as thread 1 executes, eventually it stalls either because of a cache miss or a branch mispredict. Thread 2 then begins executing. Thread 1 doesn't get control again until thread 2 stalls, so this results in a larger total number of clock cycles required in order to execute user 1's instructions. In the case of a single-threaded core, like the Ampere Altra processor, one is able to finish executions in a much more consistent and predictable number of clock cycles, meaning that each user has consistent latency. The Ampere Altra processor also has an optimized memory subsystem. The processor supports 8 memory channels of DDR4 memory at 3200 MHz. It also supports 2 DIMMs per channel, also at that same 3200 MHz speed. This allows us to provide the maximum possible memory bandwidth to feed the 80 cores in our processor. We also support a total of 4 terabytes of memory in a single socket system, or 8 terabytes of memory in a dual socket system. Now, not only does the Ampere Altra processor have high memory bandwidth, but we also need to deliver high I/O bandwidth and fan-out. The processor supports 128 PCIe Gen 4 lanes in a one-socket platform and 192 PCIe Gen 4 lanes in a two-socket platform. This is more I/O bandwidth and connectivity than any other server platform in the market. Not only do we support high I/O bandwidth and fan-out, but also our by16 controller is bifurcatable down to by 2. This means that not only do you have the option of connecting a lot of high bandwidth GPUs via our by16 controllers, but you could also connect many NVMe devices in by 2 mode for extremely high fan-out. Now, another thing that's unique about the Ampere Altra processor is that across our SKU stack, we're supporting the full range of I/O, memory, and features across all the CPUs that we produce. We'll support full memory capacity, full memory bandwidth, full I/O bandwidth, as well as all of the other features like our RAS capabilities. The Ampere Altra processor also supports C6 connectivity at the platform level for the attach of cache-coherent accelerators or storage class memory. Our philosophy when it comes to I/O has been to embrace a multitude of flexible I/O options, especially those that rely on open standards like C6. From a manageability perspective, the Ampere Altra processor supports ARM SBSA Level 4, so customers know that when they deploy our platforms, they work seamlessly with their existing infrastructure. It also has the full range of performance and thermal management features that you would expect out of a server class processor. The Ampere Altra processor also has a full range of RAS features. Now that I've told you about the Ampere Altra processor and the way that we designed it for the needs of the modern cloud, it's time to look at the actual data to prove how well it performs. The Ampere Altra processor and its 80 cores outperform the 64-core AMD EPYC processor and the 28-core Intel Xeon processor, providing leadership performance across all the performance-sensitive workloads in the cloud, whether that's AI inference, transcode, or database. When we take power efficiency into account, the lead extends even further. The Ampere Altra processor leads the AMD EPYC processor by 14% and the Intel Xeon processor by over 2x. This provides not only the scalability to deploy the Ampere Altra processor out of the edge, but it also provides the right level of performance and power for sensitive applications like front-end web and cloud gaming. Another metric that cloud service providers look at when they're assessing the scalability and density of solutions is a number of cores that they can deploy per rack. At some point, they run into a rack-level power limit, which constrains their ability to continue to deploy more and more cores in the cloud. More cores mean more users, more services, more revenue. Because the Ampere Altra processor has the industry's lowest power per core of any data center processor, we're able to deliver more cores per rack than any other solution. The Ampere Altra processor delivers over 3,500 cores per rack. That's 38% more cores per rack than the AMD EPYC processor and 173% more cores than the Intel Xeon processor. The Ampere Altra processor is the leading solution for maximum density in your data center. Total cost of ownership is also an important consideration for cloud service providers. Once again, the Ampere Altra processor leads both Intel and AMD. The Ampere Altra processor provides 41% more performance per TCO than the AMD EPYC processor and 63% more performance per TCO than the Intel Xeon processor. This is true even after the recent price cuts with Intel's Cascade Lake refresh. What's really exciting is the fact that the Ampere Altra processor is sampling now. We're proud to be partnered with GIGABYTE to bring Ampere Altra to the market. This all starts with the MP32 AR0 motherboard, which enables the full breadth of Ampere Altra capabilities, up to 80 cores, 8 memory channels with a total of 16 DIMMs with a DDR4 speed of 3200, and a massive PCIe design. Ampere Altra uses PCIe Gen 4, and the MP32 can provide 2x16 slots and 5x8 slots, with additional flexibility possible around M.2 and the OCP NIC. The form factor of MP32 is standard eATX, which makes it an extremely flexible server board. The MP32 goes into both the R272 2U single socket server series for cloud and the E252 P30 2U edge computing server. Just like Ampere, GIGABYTE is spanning the cloud from hyperscale to edge. And don't worry, there are many other platforms in the works. At Ampere, we will continue to deliver the world's highest performance, most scalable, and most power efficient processors, uniquely designed for the needs of the modern cloud. And we're excited to have GIGABYTE as a partner in building a truly cloud-native platform.